So this is what is termed as a Gauss law or Gauss theorem. Okay, just this relation phi equal to q by epsilon naught. Where is this epsilon naught? You remember it is there from the f equal to q1 q2 by 4 pi epsilon naught. It is there, right? That epsilon naught is called the permittivity of the free space. Okay, so q is the charge enclosed in the closed region. So if they say that define Gauss law or state Gauss law, you have to write this circled one, q equals phi equal to q by epsilon naught. Phi is the total flux and q is the total charge enclosed in the region. Epsilon naught is the permittivity of the free space. You are able to hear me, right? Okay, so that there is a derivation with respect to, now coming to the textbook, there is a derivation how they got this phi is equal to q by epsilon naught for a spherical region. So he considered that under the Gauss law he gives a sphere. Okay, on the sphere, this is a circle represents a sphere. Here we are taking a small area, this small area, and we want to see through that small area what is the flux passing through. Okay, so we have the formula delta phi equal to E delta S. Okay, that means through this small area how much this goes. Okay, so what will come from there? Okay, so we need to be substituting slowly. E equal to q by 4 pi epsilon naught. Okay, so q by r square also must be there, so that's equal to 1 by r square into delta S. This is a spherical surface is what we are considering. Let we consider that r equal to 1 unit. Let's consider r is equal to 1 unit. Then this becomes 1. So you will have delta phi equal to q by 4 pi epsilon naught. You can keep that 1 by r square and delta S. So delta S is only this small area. If you want a total flux, that means total flux that's coming out, that means total flux coming out of the sphere equal to, we do the sigma of the delta. That means you are considering this entire area of the sphere. I told you other day it is nothing but 4 pi r square. So you'll get q by 4 pi epsilon naught, that phi is equal to, no, total phi equal to q by 4 pi epsilon naught into 1 by r square into 4 pi r square. This is the surface area of a sphere. So this 4 pi gets cancelled. Okay, so this r square get cancelled. So what is remaining is this q and this epsilon naught. Got it, right? So that's how you get q by epsilon naught. This derivation is not required. This derivation they don't ask. There is no derivation here, but there is a next section, application of Gauss law, that they will ask. This they will not ask. Okay, this derivation is talking about how this Gauss law like phi is equal to q by epsilon naught coming, and we are giving it for a particular sphere. Okay, have you understood that? So what this says is that if you have, for example, if q is equal to 0, if q is equal to 0, that means inside a region there is no charge. There is no charge. If there is no charge, phi is equal to 0 by epsilon naught, which is 0. So if phi is equal to 0, then there is no electric field. No electric field. Obviously, right? If there is no q, there is no phi and there is no electric field. So this is what I think there are 4 or 5 observations. Okay, based on this Gauss law, what are the observations? Okay, I am in page number 34. Okay, page number 34. There is a derivation, not a derivation, q by epsilon naught is given. Then he said we state Gauss law, electric flux through a closed surface S equal to q by epsilon naught. Equation 1.31. That's important. Q equal to total charge enclosed by S. Okay. So he takes the picture 1.26 and he does it for any surface. For example, he takes it another example of a cylinder. So he considers surface like that. There is a cylinder. Now he wants to find out, there are three surfaces. This is 1, this is surface 2, this entire curved one is surface 3. So when we are considering surface 3, for example, we'll consider first surface. All this not required, is not required for the examination perspective. He is trying to say that even for sphere, cylinder, or for anything, say electric field can be 0 if there is no charge inside. Okay. So for this surface 3, this is S3 surface 3. Okay, electric field E is, okay, so this surface will be, the line will be like that, area element will be like this. That means E is perpendicular to area element. So what this means is, when we do phi 3, that's equal to E dot product. This is a dot product, delta S. Dot product meaning it comes like magnitude of E, magnitude of delta S multiplied by cos theta. If it is perpendicular, cos theta will be cos 90. So that becomes this, and delta S into cos 90 is 0. Therefore phi 3 is 0. There is no flux going through surface 3. Now for surface 1 and surface 2. For example, always that perpendicular, right? The delta S is outside only. This is the delta S for this. For this surface, delta S will be this side. Let us suppose we consider E is going this side. Electric field is going this side. For example, if E is this side, this is parallel to that. This will be anti-parallel to that. Therefore, flux phi 1 equal to E multiplied by S1. Phi 2 will be minus E multiplied by S2 because it is in the other direction, surface. So these two obviously get cancelled out. Therefore phi 1 plus phi 2 plus phi 3 is 0. Okay. So in this case also, in the cylindrical surface case also, total flux, net flux in cylindrical region equals to phi 1 plus phi 2 plus phi 3, that's equal to E S1 minus E S2. This one is 0. So totally it's 0. So that's how he starts saying that even if it is a spherical region or it is a cylindrical region or any other region, you will get the total flux to be 0. Now we are going to that significant points. They are given at the end of the page 34. Okay, sometimes they may ask for 1 mark question. So I'll be sending you today or in the next class, Wednesday, all 1 mark questions and answers, 3 mark question and answer, derivation and some numericals. I'll be sending you on Wednesday. Okay, I will go through them in the class and I'll give those things to you. Next week we will have the test in that particular, in those questions and answers only. Understood, right? You got it, right? Hello? Yeah, correct. So Gauss law is true for any closed surface, no matter what the shape and size. That's a first observation. See, this actual proof is beyond. I mean, only in the higher classes you will know. If you are interested in the electricity, electrical field, then you will know. Second one, The term q on the right side, that means a q by epsilon naught, includes sum of all charges enclosed by the surface. That's why it's a net charge. Q is a net charge, okay, not just one charge. Okay. The third point is, in the situation when the surface is so chosen that there are some charges inside and some charges outside. For example, you have a surface like this. Okay, you have a region like this. There are some charges here, and inside this there is another charge. So here no charges are there. Okay, so wherever there are no charges, there won't be any flux. Wherever there are charges, understood, right? If that net charge, for example, I have plus q, and I have minus q here and minus q here. So in this entire region, the total charge is 0 because plus 2q minus 2q. Okay. So the third point is, the electric field whose flux appears is due to all the charges both inside and outside S. The term q on the right side of the gas law represents only the total charge inside the surface S. Okay. Fourth point, the surface that we choose for the application of Gauss law is called the Gaussian surface. Okay, so in the previous case, right, we have considered that that's a kind of a sphere, and we said we are trying to see on this small area like this, and we say that flux lines going through like this. So this surface, right, that surface what we consider is called a Gaussian surface. This is a theory. Okay, there is nothing like, you can't take some copper conductor and say there is any Gaussian surface on this kind of a thing. You can't say that. Okay, so it's a theoretical concept. So on that Gaussian surface we apply this principle. So you may choose any Gaussian surface and apply Gauss law. Okay, that's the fourth point. Fifth point is, Gauss law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This is a key point. When the system has symmetry meaning, this is, for example, you take a cylinder. This is symmetrical about the central axis. Symmetry, this is a line of symmetry. Okay. So, for example, sphere also symmetrical. Okay, you take a square. This is also symmetrical. You can draw a line and you can fold it. Okay, these are called symmetrical surfaces. So, what he is trying to say is, if you are trying to find out how much flux is there, and if the body or the object has got a symmetrical shape, then the best method is to apply the Gauss law, not any other derivation. That's what he is trying to tell from the fifth point. Sixth point, Gauss law is based on the inverse square dependence on the distance contained in the Coulomb's law. That means you are actually dependent on the electrostatic force. That is what we are using, electrostatic force. Based on that, we have the electric field intensity, capital E. Okay. So this numerical what is given there at 1.11, 1.12 is based on that only, based on the Gauss law. Okay. Now we are going to section 115. Any questions you have? Do you have any? Which question? I don't have any questions. Okay. So now go to the page applications of Gauss law. So you got only 2 pages, that one. So the 2 pages questions are important. Okay. So we learnt lambda, sigma, gamma. You remember that, I suppose, right? The last class. Okay. So on page 37, first thing he talks about is the field due to infinitely long straight uniformly charged wire. So what he is trying to do is, he is trying to apply the Gauss law. Okay. So apply the Gauss law. application of Gauss law to calculate electric field, okay, on surfaces. That's what is the actual thing. So what is he doing? First one is this electric field is due to a line charge, a long straight uniformly charged wire, due to, everything has to be written, due to a long, infinitely long that means its length is infinity. Something like, as I say, I mean, if we are getting a transmission line from a thermal station to our house, okay, that is called a long electric line. Okay, so we are now trying to find out what is the electric field due to such an infinitely long straight long as well as straight, okay, uniformly charged wire. So this part is important. So everything if you look at it, right, its length is infinity and it is straight, no curve, nothing, it's a straight, uniformly charged, meaning if you take any particular length of the wire, maybe in the beginning first 10 centimeters or the middle 10 centimeters or at the somewhere at the last 10 centimeters, in that, in each of these 10 centimeters the amount of charge is same. That's what uniformly charged. Okay, so that is what we are trying to find. Now if you look at the picture, there is plus 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 plus, there is a wire he has drawn in the picture 37A, right? So he has put, I'm just trying to draw a line, that's why I'm just trying to pick it up. Okay, I think I better try a line. Okay, so you draw a line and you draw another line. So this is that charged conductor, its length is infinity. Okay, its length is infinity. Infinite length. So you are looking at the picture in the page 37. Okay, and he assumes that it's all that plus 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 plus, these are all the charges. So this is the straight conductor on infinite length. Okay, and now we are trying to find out at some point P, at this point we are trying to find out what is the electric field, and due to this conductor, what is the electric field at this point P. So what he draws is, from here, assuming it is at radius, some distance radius r, he draws a circle around that. Okay, he draws a circle. Understood? That's a radius r. So at this point we are trying to find. So this P can be anywhere. It can be at a P dash like P1 or P2 or anything, but all are the same radius. So this is also same radius, this is also same radius. Got it? Okay. Now what he says is, consider infinitely long thin straight wire with uniform linear charge density. So since it is a long straight conductor, there is lambda coming into picture. This is linear charge density. So assume that is a linear charge density of this. Is the wire is obviously an axis of symmetry. Suppose we take the radial vector the points P and P dash so obtained are completely equivalent with respect to the charged wire. Therefore, the direction of the electric field at every point must be radial. That means if you take the direction here, electric field, okay, it will be along the radius. E is along radius. Because it's a vector, we must always talk about the electric field direction. Okay. So the direction of electric field at every point must be radial, outward, if lambda is greater than 0, inward if lambda is less than 0. What do you mean by lambda greater than 0? Lambda greater than, so we know that electric field, all field lines are, they start from there and then they go outward. Correct? So this is the electric field direction. So if we are considering this as a plus, that means lambda is a plus greater than 0, then the field will be going outside. That would be the direction of E. In case you take a negative one, for example, you are considering a negative conductor, sorry, negative charges like that, then the electric field direction will be inside. Got it right? That's what he is trying to say. Okay. Yeah, you don't need everything written here is not required. Okay, this is for your understanding, right? So now what he does is, second paragraph, consider a pair of line elements P1 and P2 of the wire as shown. The electric fields produced by the two elements of the pair when summed up give a resultant electric field which is radial. This is true for any such pair and hence the total field at any point P is radial. So only takeaway from that is electric field is along radius. That's all is what we need to talk about there. Then how do we calculate the field? Second picture, what he has done, he says consider an imaginary cylindrical Gaussian surface. So you have the same thing. I am redrawing actually. You have plus, you have plus, you have plus, and you have plus, and you have plus, you have plus. Around this, he is assuming a cylindrical Gaussian surface. Okay. Important thing is that this line should be going further actually. This can't be stopping there. Right. This should be, that Gaussian surface should be smaller than the length of the conductor. Okay. That's what I mean. I extended them. Okay. So that is what he has given. So whatever you need to observe is you are considering the length of that cylinder. So length of the cylinder, I'll draw the cylinder, a better thing. Okay. Oops, sorry. So that's undo. So you have plus, you have plus, you have plus, you have plus, like that. So this is what is the picture showing there. So we are assuming this to be radius R radius. This is the radius R. And the length of the cylinder, this is the length of the cylinder, is to be L. So now at a particular point P, the electric field is like that. This is how the electric field at a point P. This is a point P. Okay. So when we say that it's a vector and we know it is at a radius R. Okay. So what he is trying to say is that at the cylindrical part of the surface, E is normal to the surface at every point. This we have derived, right? Gauss law. So if you consider this surface, this was at S3, remember the curved surface is S3, this was known as S1 and this one is S2, like previous 2 pages back we did that, right? So S3 is a curved surface, S3 is a curved surface, and S1, S2 are the other two faces. S2 or other two faces. Yeah, other two faces. So what he says now, the surface area of the curved part is 2 pi r L, because 2 pi r h is the surface area, and therefore what we have is flux through the Gaussian surface S3. So flux phi through S3 equal to, what we need is E multiplied by the area. So this area is a curved surface area. That's why you got E into 2 pi r into L. This is the radius, L is 2 pi r h. Okay, and that's what he says. The surface includes the charge equal to lambda L. So what is lambda L? The charge. Okay, so if you remember, lambda was equal to whatever is the charge divided by the length. Therefore Q is equal to lambda L. Okay, so Q is equal to lambda L. So E into 2 pi r L. So what will, now we have to substitute this into, this part is this. So we are getting to this. So Q by 4 pi epsilon naught, right? 4 pi epsilon naught. Okay, so that's what, lambda can be replaced with a Q by L if you have Q by L. Okay, so we will be doing slowly. E into 2 pi r is nothing but, okay, this entire thing is the flux. This is from this formula. Okay, but from the Gauss law states phi is equal to Q by epsilon naught. Q is nothing but lambda L divided by epsilon naught. Okay, so lambda L divided by epsilon naught. That means whatever I have here, so this phi, whatever this phi I am talking about here and this phi, both must be same. Okay, both must be same. That's why we equate this equal to this. Therefore lambda L divided by epsilon naught. Why we are doing? Because we want expression for E. So E into 2 pi r into L. So this L gets cancelled. So E is equal to, you have to bring it down. So E is equal to lambda divided by, so 2 pi r epsilon naught. Okay, so this is the expression. The magnitude is this. If you want the direction will be that n cap. He puts that n cap. If you see that 1.32, right? The direction, this is the magnitude, and the direction would be, so E is equal to magnitude, or if you put it as this, then we have lambda divided by 2 pi epsilon. I'll explain that. What is that n cap? Okay, this n cap, what we are talking about, this is called a unit vector. This unit vector means we actually had drawn that kind of an imaginary stuff, okay, and then we are trying to find here, and this E is along the radius, right? That is why this R comes there. Okay, this part is this unit vector. Okay, so if you put this, it is a vector. If you don't put and say we want a magnitude, then lambda by 2 pi epsilon naught R. So what we have done, we have derived, or rather we have used the Gaussian law, Gaussian theorem, in order to find out the electric field intensity at one point P. So what he tries to say is that you imagined this and we said this is around that line. So you can have many cylinders, imaginary cylinders, so you can find out for every point it will be like that only. So only thing that is varying is this R. The radius is what is varying. Okay, so that's the first derivation. Then the second one is field due to uniformly charged infinite plane sheet. Okay, the second one, now we want to find out E due to uniformly charged infinite plane sheet. So what is this sheet? That area charge we talked about last class. This is the area. Okay, so that's why now what he considers a small, if you look at the picture 1.30 on page 38. Okay, he considers a sheet. The sheet is something like, I don't have a surface here, I'll draw it actually. So this is like infinite sheet. Okay, this is a sheet, and this sheet has got a charges on them like that. Okay, so surface charge density of this particular thing, let us consider the surface charge density. So here these derivations, whatever derivations are not important for this first and second one. I'll be talking about the third one, that is 1.15, page number 39. That one you listen carefully, that they have given many times. Okay, so these two are easy ones actually. Okay, so he considered the sheet, and this is what is the sheet considering, and you have got surface charge density. This is the surface charge density, uniform surface charge density. So for this sheet, that much. So what he considers now, he considers that let this be, you are considering a cuboid kind of a thing, surface around this. So this is the cuboid he is considering. Okay, so this is the Gaussian surface. So this is the Gaussian surface. And now, since these are all positive charges, actually consider them to be a positive charge. If you look at it, it's all positive charge. Therefore, this field on this face, it is like this. On this surface, it will be like that. Okay, and something that will be going through the surface. So what he tries to say is that this particular case, on this surface you are seeing, right? This surface, let's suppose I call this as a, this is a top surface for the cube. So on the top surface it will be like that, on the bottom surface it will be like that. They will be exactly cancelling each other. Okay, so what we'll be talking about now is why they will be cancelling out, because this distance is exactly same. Okay, so he is considering, I will draw this one more time and then tell you. So this is the top surface. This is the top surface. So you'll have bottom surface also like that, right? He is considering that the plane is exactly in the middle. That means from here it is exactly same distance. This distance and this distance is same. The distance is same, meaning R is same. That's why these two fields up and down cancel each other. So he considers only surface 1 and surface 2. So between these two surfaces, here you consider phi is equal to EA, this side going phi, and this side phi is also equal to EA. So the total phi equal to 2EA. But that's equal to, this is from here, 2EA is coming from here. But by Gauss law, I'll get that as sigma divided by 2 epsilon naught. Understood, right? So what we need is, sorry, not sigma, we have q, isn't it? Q divided by epsilon naught. How do we do q here? Is 2EA, E, area of this equal to maybe the square area or whatever you can consider, x and y. Okay, so that area can be constant area anyway. So 2E multiplied by area equal to my surface charge density, okay, into area divided by epsilon naught. So q by epsilon naught. That's why this comes like this, right? So I need to get, are you with me or confusing? Okay, yeah. So we need to get the expression for E. So E is equal to, area get cancelled, sigma divided by 2 epsilon naught. Okay, so that's the answer. Okay, so in the previous case it was lambda divided by 2 pi epsilon naught r was there, electric field. Okay, in this case you got sigma divided by 2 epsilon naught. Why 2 pi was there in the previous case? Why we don't have 2 pi in this case? Because that is a cylindrical surface. Cylindricals and all curved things, right? You get pi. Here no pi is there. Got it? Okay, yeah. So for finite large planar is approximately true in the middle regions in the planar sheet away from the ends. The next one is the important one that has got many cases. One is field outside the shell, field inside the shell. Two cases are there. Okay, so what is a shell? Now the third one. Go up. Yeah. So now we are considering the third one, E, okay, due to uniformly charged thin spherical, due to uniformly charged thin spherical shell. So what's a spherical shell? See, let's suppose you have a golden bangle, okay, golden bangle of some thickness, right? We wear a golden bangle of some thickness like that. That is not spherical, right? A spherical good example is a tennis ball. So there is a little bit of rubber thick. This is the thickness of the rubber and it's entirely spherical, isn't it? So it is called shell because you have that rubber thing, right? So this is all inside. This is that inside that rubber. This is outside the ball. Understood? Okay. So that's why he starts considering field outside the shell and then field inside the shell. Two pictures are there. It's not a big derivation, it's easy derivation. So look at the two pictures. Okay. So this derivation I will be sending you as a separate page. Okay. So I will be explaining directly from the textbook now. Okay. So you are seeing the first picture. Assume the radius to be capital R. And let us suppose we have a point P on the dotted line circle. The dotted line circle is a imaginary thing. So you have this picture and this is a capital R. This is this one and you have a dotted line like that. And let's suppose you have got point P here. Okay. So that is at a distance R. Okay. So from here the distance is of this is R, total distance. Okay. So we have already seen that if this is all a spherical shell, okay, if this is a spherical shell, then surface area of a sphere of sphere is 4 pi r square. What is the sphere? This is a Gaussian sphere. Okay, this is Gaussian sphere. Therefore, E into 4 pi r square, like last time. Okay, that's equal to, so whatever we did, sigma by epsilon naught into 4 pi r square. Okay, so E into 4 pi r square, what is this? This is phi. Correct? So that's what is that phi. How do we get the phi to be? Sigma by epsilon naught. Okay, so that should be q divided by 4 pi r square. Okay, so q divided by 4 pi r square should be here. By Gauss law, this is nothing but whatever you have, q divided by epsilon naught. So in order to get the q, okay, we are replacing that with the sigma into area. Sigma into area is nothing but 4 pi. This is a step you need to understand. He uses 4 pi r squared. I replaced q with this. How? Because of that last time we said, right? Sigma is nothing but q by sigma is nothing but q total charge divided by the area. This area, because you are saying only this much, right? Charge is enclosed in this. Okay, that's why this becomes, and therefore E is equal E into 4 pi r square equal to sigma by epsilon naught into 4 pi capital R square. So this 4 pi gets cancelled. So what we have is E is equal to sigma r square by small r square by epsilon naught. Okay, so this is how you will get E is equal to either this or replace sigma with your normal. Sigma is equal to q by 4 pi r square. All that 4 pi gets cancelled, and therefore you will get as given in the textbook. So what we have got is equal to E is equal to sigma by epsilon naught r square by r square. So if I replace sigma is equal to q by area is 4 pi r square, so 4 pi r square, then you will get q divided by 4 pi capital R square and epsilon naught into r square divided by small r square. So this r square get cancelled. Okay, so you will have that's equal to q by 4 pi epsilon naught r square. This is the, got it? So this is the one for the inside the field. You field outside the shell considering this capital R. This is the field outside. Now for the second one, field inside. The field at P inside. That means you have got this ring like last time. Now you have to consider the circle inside here. Got it, right? That's the only difference. So inside that is a small radius r. This is a small radius r, and this is the capital radius capital R. Okay, so field inside the shell, the point P inside the shell, the Gaussian surface is again a sphere through P central at O. So now what happens? Now we are talking about what is the field enclosed. Okay, so is there a charge inside R? There is no charge inside. No charge inside R. This is the smaller circle, okay, inside R. Therefore, E into 4 pi r squared, okay, is 0. Why? As per no charge, okay. Therefore, E is equal to 0. That means inside the field is 0. That's all we'll be writing. This is the derivation, 2 parts, okay. This is the important stuff. So let's go through one more time. Okay, so we are done with this chapter. Okay, but I'll go through as like last time. I'll go through one full round of this whatever we covered today, right? So this is the first topic. I said we learnt a relation connecting electric flux, electric charge and area through which the flux lines pass through. So that's what we actually learnt. That is nothing but E is equal to lambda by something, E is equal to some. So that was the relation I talked about. This is the relation I talked about there. Okay. The Gauss law states that the flux inside a closed surface is given by the total charge enclosed inside the surface divided by the epsilon naught. Epsilon naught is nothing but, we know the epsilon naught. Epsilon naught is a permittivity of free space. So I think I better write it rather than typing it. So this one, permittivity of vacuum or free space, right? So Q is the charge enclosed in the closed region. This is what the Gauss law or Gauss theorem. Proof not required, but we are actually trying to consider a spherical surface and a small area on that sphere. That means like on our scalp or a skull, we are considering a small patch, okay, on our skull like that. So we know that the delta phi in this small area, is given by electric field. The electric field would be perpendicular in this particular case. Here the electric field will be going this side if the charge is positive, Q is positive. So E dot delta S. So E is given by Q by 4 pi epsilon naught R square. This is all the E dot ds. So from there I continued the same step here. So the total flux is given by sigma of all that small areas put together. So that's what this particular thing, from here we have gone. Okay, so Q dash, not Q dash, I think this is not there. So we only have Q. So it's so sensitive, so I just need to be putting, yeah. So Q by 4 pi epsilon naught 1 by R square. Because it's a sphere, I consider 4 pi R square. R square and 4 pi get cancelled, so you get Q by epsilon naught. And this is the Gauss law proving for a small sphere. So we can't be doing this for every surface and all. So that's why they consider talking about a surface which is symmetrical in nature. Okay, so if Q is equal to 0, that means inside a surface, inside a region, if there is no charge enclosed, then the flux phi is equal to 0 by epsilon naught, which is 0. That means there is no electric field. Next he considers a cylinder. So he considers a cylinder. For cylinder, so he says you have three surfaces, surface 1, surface 2, surface 3, and if you assume that E is in this particular direction, so for phase 1 and phase 2, E gets cancelled, or rather the flux gets cancelled. Phi 1 and phi 2 is equal and opposite in direction. This is this side, this is this side. So therefore we have to consider only for curved surface. That's a phi 3, and that's equal to also 0, because the angle between the theta is nothing but the 90 degrees. So theta is 90 degrees, theta 90 is a 0, therefore field is 0. phi 3 is equal to 0. So all phi 1 plus phi 2 plus phi 3 equal to 0 even in this case also. Okay. So the net flux equal to 0. So symmetrical surfaces is what is easier for the Gaussian, use the Gaussian rule or Gaussian theorem or Gaussian law. Okay, so he goes with that concept and first application of the Gauss law. So the question will be like this only. Using the Gauss law, derive an expression. Okay, derive an expression for electric field intensity or E. Okay, so that is how the question will be. So now first case is electric field due to an infinitely long straight uniformly charged wire. This is that uniformly charged wire and we are trying to find out at a point P how much is the electric field. Okay, it is of infinite length. So E is along the radius, that means E will be along the radius and will be outside, will be getting outside because it's a positively charged. Okay, if it is a negatively charged, E will be inside. So we have considered a Gaussian surface. This is an imaginary surface, cylindrical surface in which this wire is placed. We are assuming like that, and therefore we apply the same thing like S1, S2, S3. In the previous case, S3 was through S3 it was 0 because there was no charge. Now in this case it will not be 0. S1 and S2 are the two phases, they get anyway 0 here, S1 and S2. So through S3 is equal to E multiplied by area. Area is the curved surface area, is a 2 pi r L. So we are coming from phi is equal to E into 2 pi r L through this, which is not the Gauss law, but the Gauss law is Q by epsilon naught. Q is replaced by lambda L by epsilon naught. So we are equating this from the Gauss law and E equal to 2 pi r L. So L gets cancelled, E equal to lambda by 2 pi r epsilon naught. Okay. Then if you are considering as a vector, then you put this unit vector, which is unit normal. Second case is E due to a uniformly charged infinite plane sheet. Okay, it's an infinite plane sheet. So you consider this sheet and we assume that the up and down, okay, it is exactly in between this imaginary cuboid surface, Gaussian surface. So this distance and this distance is same. E is going upward and downward. The top surfaces and bottom surface E gets cancelled. Now we have to talk about going this side and this side. So we have 2E into A or E into 2A, this area and this area. This is not by Gauss law, this is by Gauss law, Q by epsilon naught. So we replace Q with a sigma A gets cancelled, E is equal to sigma by 2 epsilon naught. Again replace sigma now with the area. Sigma, I think sigma 2 epsilon naught is correct. For the spherical one we replace it. Okay. So the third one is E due to a uniformly charged thin spherical shell. So this is the shell. Consider the tennis ball kind of a stuff. So two cases, one is inside this shell here and the other one is outside. So first we are considering, so surface area E due to the uniformly charged sphere we are considering. So we are assuming outside this particular thing, outside this entire area, an imaginary surface, that's your Gaussian sphere. So surface area of sphere is 4 pi r square, therefore E into 4 pi r square is by not by Gauss, this is by Gauss, Q by epsilon naught. Then you get sigma into 4 pi r square by epsilon naught. So finally you get a relation E is equal to sigma by epsilon naught and capital R square by small r square. So you can replace that sigma equal to Q by 4 pi r square. So you get E, electric field, exists outside the sphere. This is the electric field outside the sphere that exists. So this is outside, any point outside sphere, any point, yeah, outside. Okay. So the next part is inside the sphere, field at P side. There is no charge enclosed inside R. Why? Because the charge is everywhere outside only. there is nothing, no charge here. Okay, the charges are here in this space, and therefore E by 4 pi r square is not by Gauss law. By Gauss law, total charge enclosed, that's Q, which is 0, therefore 0, and hence E is equal to 0 inside. Okay,